All right, so welcome back from the coffee break. So the first talk after break will be from the Frankfurt group given by Hendrik. So please go ahead.
Yeah, hi. Today it's about heteronization, and as was told already from other talks this afternoon, also in the Frankfurt group, we used the standard coalescence model using this Wigner function with from Gaussian Wigner function with the sigma squared related to the root mean square radius of the D meson. And yeah, everything which does not coalesce, of course, must fragment, as in all the other models explained so far too. And also we have a pretty small coalescence of 20% or so versus fragmentation. And then I want to present a calculation we did some years ago to predict what happens at fair energies. Maybe they measure heavy quarks there. And then, of course, you need also hadronic transport coefficients. So this will be the first part. And there we used the also already quoted model from Abreu et al. And Laura Tolosch et al. And it's based on a coupled channel T-matrix approach with the pseudo Goldstone mesons in the light sector and also baryons. And the D meson scattering cross sections from this model is then used to calculate the heavy quark track and diffusion coefficients in the usual way. And what comes out there are pretty small track and diffusion coefficients. But yeah, and now we want to study how this works at the lower beam energies to be expected at fair. Also here some more. This is from the baryons and this from the mesons. Of course, both we use both together. And also, of course, at finite mu b, and then usually you have more impact on D bars than on Ds in the scattering. And yeah, the D mesons at fair, we use a kinetic beam energy of 25 AGeV. The bulk medium evolution was used, this UQMD, one model was UQMD hydro-hybrid approach, because of course we always need a temperature and chemical potential to do our Large using the calculated track and diffusion coefficients. And another model, maybe a bit more realistic at the lower energies, is to use UQMD for the bulk medium and then use a coarse-graining approach to determine temperature and chemical potential. There we used asymmetric hydro and anisotropic hydro model to fit the spectra from the UQMD to temperatures and chemical potentials. And this heavy quark transport coefficients in the QGP, these are taken from our good old resonance model. And what I want to concentrate on here is now the influence of the hadronization description, the sensitivity to the hadronization temperature. You can, of course, you can speculate where this hadronization temperature should be chosen at this lower beam energies and compressed baryonic matter, and also coalescence versus fragmentation. And there we play with these parameters, this RD, this root mean square radius of the D meson, and this epsilon p in the Peterson fragmentation function, which determines the fraction of the momentum from the heavy quark to the D meson. Here is an RAA. This goes up for higher PT, because there is, of course, the energy constraint in the low energy fixed target. There the PT in PP is around less than 2.5 is a constraint. And that's why these go up. And also, of course, this I don't want to go into, but it's all in our paper. There's of course a great uncertainty also in the PP baseline, because nobody knows how the PP baseline for D-meson production looks. Here I show an example where one uses Pythia and for charm quarks and fragment them into D-mesons as a baseline. And there you see this is for the hybrid where the QGP evolution is switched to a hydro evolution, as compared to if you use this coarse graining. And there you see generally, of course, in the coarse grained bulk medium is less thermalized than the hydro, which is in local thermal equilibrium. So you have less flow also than with the full hydro. Okay, let's look at the V2, and there's the first the first hadronization question is I use different hadronization temperatures. The both figures are always for impact parameter 3 Fermi and the more semi-central collision at 7 Fermi. And there you see, of course, because the QGP transport coefficients are much larger than the D-meson drag coefficients in the hadronic phase. If you switch at lower temperatures, you get more V2 from this QGP phase. Again, here the comparison, this is the hybrid model with the hydro evolution for the QGP, and this is for the same parameters in the coarse graining. So you see there is again this effect of less thermalization of the medium, so you get less flow to begin with. Yeah, this is another thing in the one has different overall lifetimes of the simulation, whether you use the hydro or the coarse graining. For the hydro, we switch at some given energy density. We switch from QGP to, or no, we thermally freeze out, and the coarse graining we just let run for 75 Fermi. And if you now use in the coarse graining also the stopping time of the hydro model versus the full run, this is the long run is you let it run fully for 75 Fermi, and the short run is you stop the Langevin at the same time as you stop it at hydro. And there you see nearly no impact for Ds and D bars. So the later the hadronic diffusion doesn't do too much in our model, because the these track coefficients are pretty large at low temperature, pretty small at small temperatures. Okay, this is now the study what changes if you change your parameters of the hadronization model. This is a study, this epsilon p. This is in the Petersen fragmentation. We vary it between 0.05 and 0.01. And also this RD in the coalescence, the standard value we choose from the Greco-Corrupt paper of 0.6, and here we change it also to 0.9. And there you see this gives large differences here. Of course, the full black line is just the charm quark V2 before hadronization. And of course, the coalescence always brings your V2 up pretty much because the D meson inherits the V2 from the light quarks. And there you see how was it if I change the RD from 0.6 to 0.9, I go from this orange line to the to this lower blue line, and this is of course the impact of the coalescence probability, which goes down when I put up this D, and also when I go from 0.05 for the epsilon p to 0.01, I also get lower. So there is a large impact on the hadronization procedure, how I choose these values. And what was the last one? I think I'm done. And what I just wanted to say is perhaps one indeed needs a more elaborate hadronization procedure, like what Min He mentioned, this resonance recombination model, which would of course also be consistent with the resonance model used to calculate the track and diffusion coefficients. And also it obeys energy momentum conservation and also the second law, because it's just another kinetic process. So I think it's a good idea to refine our hadronization procedures to something more fundamental, or how you want to call it. Thank you very much.
Thank you, Hendrik. So now we have time for questions. Rob?
Yeah, really quick question. So naively, you would expect that if you have a larger radius, you have more phase space for coalescence, right, in coordinate space. But your V2 shows the opposite. Is that easy to understand?
Yeah, but you have your if I understand it right, with your sigma getting larger, you have smaller coalescence probabilities, right?
Yeah, that seems to be so.
So that's why that was my explanation why this happens.
Right, but sometimes in the literature there are arguments made that if the radius is larger, you get more coalescence, right? Because
yeah, that's also true.
Exactly opposite here.
Yeah, that's true.
Thanks.
Any more questions or comments, Peter? Peter, please go ahead.
Just a second. I need to turn my microphone on. So just a little comment to 25A GeV energy at fair. I think it's a bit unfair not to mention in this context SPS and NICA, where energies are will actually be achieved, while in fair for the next 20 years, I don't think so. There is no 300 that doesn't exist.
Yeah, that's true. Perhaps I should just write.
You can leave fair in there because it's considered a future facility, but I think it would be
fair to mention the others. Yes,
from NICA and SPS where such energies are available very soon or already now?
Yeah, okay. I will do it next talk.
Any more comments or questions to Hendrik? I didn't see any. So thanks a lot for the presentation. So I suggest we move on to next talk and to post talk for next group.
Okay, so Yenji, so is it not now?
Yes,
Okay.
I haven't. I don't see the screen yet. Please share the screen.
No, but I thought it was Duke in the agenda, but okay, no problem. I will share my screen.
Okay, yeah.
Do you see my screen now?
Oh, not yet.
Not yet.
Now I can see it.
Okay, perfect. Okay, so thanks a lot for giving me the opportunity to explain a little bit how we proceed with hadronization, and also one slide about here's the hadronic matter. And basically, we do a bit like most of the people around. So we have some coalescence plus fragmentation approach. Up to now, we have no variant. I mean, this might come in the future. And what I want to insist here is some recent update that we have made since the ME Rapid Reaction Task Force. And in the near future, basically, I would like as well, a bit like Hendrik, to develop something that will be a bit more rooted to the deep interaction around TC. But right now, we use coalescence. So typically, there are two physical pictures for coalescence. So the one where we rely upon is that basically we have one heavy quarks here and one light quarks that come out of the quark-gluon plasma and then instantaneously merge, okay, according to this Wigner distribution. So we take a delta distribution here for the heavy quarks, and here we take something that is locally thermalized for the light pattern. But even with this general formula, then basically you have here to look how to model this Wigner distribution. So there are several guidelines here by our fathers in the literature. And what was important to us is to realize that this formula here contains 3 4 vectors. And so if you want to deal it relativistically, then you really have to take the 3 into account. And there is no reason why, except in some special situation, they should be aligned. So basically, we really keep track of the direction of all these vectors. And now going a bit more into the details, I think you can get, so now we're really speaking about relativistic modeling of the Wigner distribution in terms of relativistic invariance. What you find in the literature is that you might write it as a function of here, this distance in Minkowski space, but we preferred here to have it expressed basically as a special distance in the reference of the Q, basically. Otherwise, if you make it in the center of mass, it makes the math a bit difficult once you want to integrate on the spatial position. Then basically this we have kind of introduced in our PRC review, and once you integrate on the space, then on the local space around the Q quark, then it brings this extra factor here in the denominator. Then as for the momentum space, there are also different models that you can have in the literature. And we basically have this Gaussian in P space. But what we prefer here is to have this dependence versus the 4 velocity of light and heavy quark. with this reduced mass here, plus this parameter that reflects the strength of the interaction. And then with this, you have some semi-analytical formula that you apply locally. So we fully conserve all correlation between space and position. And we are then able here to provide absolute numbers for the coalescence. And then the rest basically is a pure question of how to fix the parameters, so that you have here the large mass quark as well as this width here. And for historical reasons, basically, we had then this probability was tuned on the B. So we kept basically the same alpha parameter. So basically it means the same width here for both B and D. Not the same strength, sorry, for B and D. And we tune this parameter here such that the probability to coalesce a B quark into a B meson was a unity for zero momentum, assuming here that U cell and D sigma are parallel. And as for the light quark mass, we had some freedom, and we had also some historical model. And for the purpose of fitting our historical model, we have chosen, it was probably a bad choice, a rather small light quark mass here of the order of 100 MeV. And so this was typically the summary at what we have done in 2009. And then basically, once you go now really on the full-fledged model, you realize that the probability to form a D meson here is a product of this probability here that takes place when both D sigma and U cell align times this flux factor that embed here all these four vectors. Then basically we go now for the full hadronization algorithm. It took us a couple of years to realize that one needed to perform a clever choice, namely that the fragmentation, you decide everything basically in the fluid cell. It is where the things are the simplest. You also make the coalescence in the fluid cell. But if the result of your dice sampling is fragmentation, then what you need to do is you need to perform the fragmentation in the lab frame using the so-called PT fragmentation. And it is what guarantees that if you start from one distribution of heavy quark that is boost invariant, then the same is true as well for your D meson, and also that you do not communicate some kind of extra boost passing from the fluid cell to the lab when you perform fragmentation. And this is typically what we get as a ratio of D meson between heavy ion and NPP once you turn the energy loss off. So this is the sole effect here of the coalescence typically. And you see this large flow bump. Now, of course, basically, if you turn on the energy loss, then you will get a reduction of this flow bump. Nevertheless, we still see some results of this coalescence. So at RIC, it is really manifest here that if you look at the array of D meson with respect to C meson, it really appears. And the same is true as well at LHC. These were preliminary results without shadowing, and especially for the B2, it has a large. Then came this ME workshop when we compared things between us. And what was realized at this workshop that looking at this HAA, which is here the ratio of hadrons, so D meson with respect to C quark, then basically we had here the largest HAA, and the possible reason that was advocated was that this light quark mass was chosen too small, which makes it possible in the global cocktail to compensate for larger energy loss. So it is a bit the same effect that Catania has found, meaning that if you input a strong coalescence, then basically you got a bit, you get lower in this 2 pi, and then what we wanted to do since is basically to adapt a model in order to see whether it is possible to join again the group. Also at this workshop, it was realized that there might be some possible issues with violating an energy or entropy, and that a good constraint would be to advocate from equilibrium limit if you start from a situation where both heavy quarks and light quark are themselves in equilibrium. And then we first performed some study with the model we had at the time. So basically, these lines here are the Cooper-Phi spectrum that you can find for assuming basically some arbitrary d meson masses. And you see that if while combining light quark of mass so 0.1 and heavy quark here of mass 1.5. And then basically you can of course pretend that you have a rather good agreement provided that you take a d meson mass of 1.9, but this is in the log scale. And now if you make the real ratio, then what you see is that in fact the agreement is not that good. And I think it would be fair that when we plot this kind of agreement plots, basically we do not provide simply the full spectra here, but really the ratio. And but this was with this Dover spatial dependence. And now if we take now our spatial dependence, which is not this radius in Minkowski space, then you see that there is one equivalent d meson mass for which we get exact calibration on the Cooper-Phi emission formula. Now, to be fair, we don't know exactly why it is the case on dynamical grounds, but at least what we can guarantee is that if the parameters are chosen in such a way that the ratio here is strictly unity, then at least we will mock this equilibrium situation first, and on the second side, the effect of coalescence would not depend whether you perform the coalescence in the lab or whether you perform the coalescence in the fluid cell, as it is right now the case. And once you have made this parameter choice, then you see that you can also vary here the fluid velocity. It was taken at 0 in the previous plot, but here we take a different velocity for the fluid profile, and still you get really a good agreement with this Cooper-Phi spectrum. Then we did this basically, so we claimed for the best parameter, which can on the one side here lead us to a correct agreement with the Cooper-Phi reference spectrum, and on the second side that could lead to 50% coalescence of C quark into a d meson at p equals 0, the other 50% being converted in a mind to a barrier. And these are the new parameters. So still for the model, which has been left unchanged, but now with this new parameter, we are closer to what other groups obtain as well. So we are around 300 MeV for the light quark mass. Then what you see, if for instance we compare the absolute probability, then this dashed here was basically the previous parameter choice. And now with this new set for a given P, then the probability to coalesce is smaller typically. And then there will be, of course, some consequence on the array. So one should compare here the red and the blue. So you see really a reduction of the array. You see as well here a reduction of the HAA as compared to what was shown at Hemi. And Then basically, I think I will skip directly here to the new implementation in EPOS. So with this new parameter set, then typically with the previous implementation of our coalescence plus hadronization, this rescaling factor we had to apply to fit the data at 10 GeV, where typically 1.8, and now basically with this new set, we still find the equivalent agreement with reducing slightly by 10 or 12% the strength of the interaction. So it means that it makes our interaction a bit less coupled, but still the difference is rather mild, I would say. As for the consequence for the V2, so due to the fact that this strength is smaller, so the C quark V2 is reduced a bit. And as for the D meson, we have basically the same V2 for the D meson, but it kind of decreases a bit faster here at a large PT, what seems to be compatible with the data. So basically, so we have shown the consequence of fitting at best with this constraint of reproducing this Cooper-Frye spectrum. So in the short-term future, we would like to generalize this hadronization model for the production of DS and lambda C, and probably trying to compare as well with other parameters from other approach. While we feel that at longer future, we need a formalism that is more deeply rooted to microscopic principles. And as for the role of the hadronic phase, so we have some preliminary EPOS HQ, which is a coupling of EPO3 plus approach here, plus UR QMD. And then you can see by yourself, by comparing the dashed here with the plain line, what is the role of the hadronics interaction in UR QMD. There's also a cross-section that were provided gently by Jan Steinheimer in UR QMD. That's it for me. Thanks a lot.
Thank you, Paul. Now we have time for questions. Rob?
Sorry if I'm always asking questions. Well, very interesting talk. Actually, it brought to light something which I didn't appreciate before. And if you can go back to the EMI plot that you showed, I really appreciate it now that you do have, if I understood correctly, space momentum correlations even in that earlier setup. Is that correct?
We had them from the beginning, Ralph, yes.
Yes, so that may very well be one of the main reasons why your HAA is shifted out. I can tell you, for example, if we include the space momentum correlations in the TAMU model, which is the blue line, they would definitely shift it further out. So that may be actually the main reason, although it has been a little bit mitigated now with your new implementation, but you know, these space momentum correlations really play a role in that 4 to 8 GeV region.
It's a very good point, Ralph. In the end, so the main message indeed that despite all the work that we have done in order to readjust this light quark mass, we are still above the others, quote unquote, or at least above many others, basically. So we need to find the reason why. Yes.
Yes, I actually noticed this already from first day. When you plot this, it looks like different model somehow are clustered in two groups. Has anybody actually looked at what is the common feature of these two groups of models? Why they are?
You mean here?
Yeah.
Yeah. Those ones not have coalescence, basically.
Oh, this
I guess.
What?
Those ones here.
So those lower that has no coalescence, everything have coalescence above, right?
I think so. Yes.
Oh, okay.
No, it's not like this. No, like at the high PT, whether you have coalescence or not, you should tend to the fermentation only, right?
Yeah, I was thinking about this at this high PT, the coalescence is not going to play any role, right?
Yeah, but I guess this really depends on which time of fragmentation you take. Okay, so we take kind of Peterson fragmentation, or we take FONL fragmentation, and
exactly. Could this because this is different cluster models, they use different fragmentation functions somehow?
Well, we need to compare.
Yeah, maybe we can come back to this discussion again later. Yeah. I think it will be interesting to find out.
Yeah. For LBL, CCNU, Shanshan already explained, right? This line, this red line, is quite low. It's due to the mass using
there are too many colors. There are too many colors. I cannot really tell which one is which. So maybe we can.
The purpose of my talk was not to remind you about Emmy. Okay, was to tell you what we know.
Yeah. Well, thank you. We will come back again.
So Paul, in the new compilation for the workshop this time, the new HAA definition. So it seems to me at high PT, the Nance models give rather small HAA values.
Yeah, but it's not the same HAA. We have to be careful because it's not the same HAA. Yes. We will discuss this at the end of the day. I have a compilation of all the work that people have done, and I think we will take time to go through it. Yes.
Sounds good. Yeah. Any more comments or questions? Yeah, I think it would be interesting to compare not only the new HAA, which is the IA ratio of the hadron and quark, but also the HAA as defined in the ME setup, so that we can separate the effect from PP and LELEC or and AA, for example. Okay, thanks a lot for the discussion. So so let's move on to a Duke group. I don't know who is presenting today.
Oh, I think I'm presenting.
Okay, please go ahead and project the slide.
Oh, okay. How can I?
Now I can see your screen.
Can you see the slides?
But it's not in full screen mode.
Oh, all right. Okay. Can you see it now?
Yes. Please go ahead.
Great. Okay. Hello everyone. My name is Wen Kai, from Duke, and again, I will be presenting our results on heavy quark hadronization and hadronic ring scattering, based on works of one of our former group members in RU. And because our study is mainly focused on comparing to experimental data, we didn't focus much on hadronization, on the details of the hadronization, which is mainly done by other people. So let me just remind you of how we study the full heavy ion collision process. So first we have our initial conditions, and then we have our soft medium evolution and heavy quark transport, which for the soft medium evolution, we have our Bayesian analysis to comparing to bulk medium observables. And then we have hadronization, which is a combined model of recombination and fragmentation. And lastly, we have hadronic ring scattering phase using the UR-Kimberley model. And to compare to heavy flavor observables, we again perform a Bayesian analysis, after which we extract the model parameters here. So using those parameters, we can generate the momentum distribution of heavy quarks right before the hadronization. So, and for hadronization in AA, we have fragmentation. Now we have fragmentation done by PCA plus a combined model of recombination and plus a recombination model or coalescence model. So this model assumes that those heavy quarks are suddenly coalesced into mesons and baryons, and the mechanism is very similar to what Shanshan has presented a few presentations ago. So the momentum distribution of mesons, of heavy mesons and baryons are described by these two formulas, where this dn1 over d3p1 or dn2 over d3p2 is the momentum distribution of quarks, where if this is a heavy quark, its momentum distribution is determined by the medium transport, where if it is a light quark, it is determined by a thermal distribution, because we assume that those light quarks comes from the thermal bath or the thermal medium, and this FWM and FWB functions are the Wigner functions, and if we assume that the wave functions of those quarks are of a Gaussian form, then we can simplify those Wigner functions to those expressions. And for example, for the meson Wigner function, the Q this Q represents the momentum difference between the two quarks, two constituent quarks. Sigma is this expression, where mu is the reduced mass, and omega is the oscillation frequency, determined by comparing to the charged radii of the corresponding charged meson or baryons. And to simplify the problem, we only compare to a few species. We only use a few species of the charged radii data to calculate those omegas, and we have omega equals to 0.33 for charmed and beauty mesons, 0.43 for charmed baryons, and 0.41 for beauty baryons. And so after determining these omega values, we can calculate the probability of coalescence for both charm and beauty quarks. So the black and green lines are the total probability of coalescence into any hadrons, and the blue and red lines are the probability of a heavy quark coalescence into a either a D meson or a B meson. And after that, we have the hadronic risk scattering phase, which is simulated by the UR-Kimberley model, which has this collision term that includes binary collisions, inelastic processes, etc. And we assume that binary collisions would happen if two particles are close enough in the phase space, determined by their distance, which is controlled by the total cross sections of the collision. And so this is the main results for comparing for telling the effects of hadronization and hadronic risk scatterings. So the green dashed line is the RA and V2 for charm quarks. The blue solid line is the results just right before hadronization, right after hadronization, but before before hadronic rescattering, and the red line is the final results. So we can see hadronization enhances the RAA and also the V2. And then hadronic rescattering reduces RAA at high PT that further enhances V2 for almost all PT ranges. And this calculation is done using just a set of optimal parameters extracted from our previous Bayesian analysis. So that's why the final results is comparable to the data. And this is the results of HAA and HV2. Basically, the ratio of the blue line and the green solid, the green dash line. And you can see indeed the demeso RAA is enhanced compared to the charm quark RAA, and the V2 is not much influenced at high PT, but is quite enhanced at low PT by the effects of by the effect of coalescence. So the purpose of our study is to try to fix other ingredients of the simulation by Bayesian analysis, so we can single out the effects of hadronization and hadronic rescattering. And that's all for my talk. Thank you.
Thank you very much, Wenkai. So now let's take questions to Wenkai's talk.
Hello, Yanji. I have a question, but I don't have a hand. Can I ask one?
Yes, please go ahead.
Wenkai, I think on one of your slides, you in the coalescence model, you were using a certain wave function or distribution of mesons. How did you actually get the width of the mesons? Did you calculate it? Did you make an assumption? Or maybe I'm misinterpreting that this is the width of the mesons and baryons.
Do you mean the Wiggin functions?
Yeah.
I see this sigma is expand in this later slide, where this omega is, so the parameters are mainly this omega, which is determined by comparing to the charge radii.
Okay, so you use some experimental measurement and then parameterized.
Yes.
Okay, thanks.
Any more questions, comments? Ralph?
Yeah, I would have one comment. If you come back to your systematic studies of the hadronization and hadronic phase rescattering. And this is not at all specific to what you're doing, but it's a general feature I think that everyone should be aware of. See, if I understood correctly, what your coalescence does, it actually increases the RAA even at high PT, right? Is that true?
Yeah.
So the blue line rises even at high PT. And that is really, and again, it's not specific to you. That's specific, however, to the coalescence implementation. That violates the second law of thermodynamics, because the coalescence is driving away the spectrum from the equilibrium limit, which is of course way lower, right? So a coalescence model that satisfies the second law of thermodynamics should actually reduce the RAA at high PT. But again, not specific to your calculation. It's a general problem with many coalescence models.
I see.
But this is also in the TAMU calculation, right, Rob?
Excuse me?
This is also in the TAMU calculation, right? So
no, our coalescence should bring it down because it drives it toward the equilibrium limit. Is that correct, Min? Or?
Yeah, because if I look at the HAA compilation, so at something like 10 GeV, so the TAMU is still
which HAA that is, right? If you look at the old HAA,
the new HAA.
If you look at the old HAA, it's actually going down. But you know, I didn't even want to make a specific comment to that, but whether this model or that model, but it's something we should be aware of, that this is not what in principle should happen, that the coalescence increases the RA, because coalescence is just another interaction, and it should drive the spectrum closer to equilibrium. That's the second law of thermodynamics, right? And if it doesn't do it, it violates it. And no matter which model, all models should in principle, you know, maybe improve that.
Thank you, Ralph. Jinian?
Yes, this is I think this, I have this question again. I don't really understand how the coalescence can affect the spectrum up to 30-40 GeV. That I really don't understand, because normally the coalescence only with thermal partons that roughly has same kind of momentum with the leading parton.
It's the same velocity, not the same momentum.
Yeah, at same velocity, yeah.
I mean, simply, I think what Xinyan is saying is there are too few partons, even if they accidentally are aligned, there are just too few of them.
Yeah, that means this should be, I mean, apparently it's still dominated by fragmentation, but I'm really surprised that the coalescence still have such a significant effect at this high PT.
Hi, can you hear me?
Yes, Real.
Oh, yes. So right now we are comparing the green line and for example the blue. I think in this case that the blue line, which is after the hybridization, is higher than the Charmar array. There also a reason is that you have due to fragmentation, you're actually shifting the green line from high PT to slightly lower PT. So I think most of this increase from the green to the blue are actually due to this shifting loss in PT in the fragmentation. To really see what the recombination does at high PT, I think what we should compare is turn that off and compare the RA of D meson and turn it on. In that case, at least in my calculation, I don't see such big difference at high PT.
I see. So
sorry, turn what off? I don't understand. What else?
So what we should compare to see the effect of recombination is turn recombination on and off in our model and compare our for D mesons. But here you can see that it's the green lines for charm, which is before fragmentation. So after fragmentation, you will also lose some energy. So you're shifting from the high PT points in the green line to a slightly lower PT. Which visually looks like the line is increasing.
Yeah, that's exactly right.
Yeah, I think this can be easily checked to see whether.
Yeah, thank you, Wei Yao. In the rough bringing this point, I think a conclusion from here is that we need to compare the result with and without coalescence in the same observable, which is the D meson. Then we can show this effect directly. Any other comments, questions? If not, then let's thank Wenkai again. And let's move on to the next talk, which is from the SCAT group. Ivan, are you giving the talk?
Well, since I'm doing the calculation, You know, the SCAT group is me. Other people are working on other things. So okay, so the practical question: can you see the can you see the screen?
I can see your screen, but not
okay. So now let's go into full mode.
Now it works.
Okay, so again, thanks for the organizers for the opportunity to continue the discussion on SCAT. So just as a reminder, SCAT stands for, or SCT stands for Soft Collinear Effective Theory. This is an effective theory of QCD designed to describe jet physics. It can also describe heavy flavor physics when the heavy quark mass is appropriately included. And as a reminder, last time means yesterday, we discussed that it can be generalized to describe the propagation of energetic partons, heavy or light quarks in matter. And it can derive the splitting functions, the full in-medium splitting functions, which go into higher order entry sum calculations. It can also be used to take the small x or soft balloon emission limit, in which case we have the traditional energy laws that we have been using, you know, maybe 10, 20 years ago. Now, on to the subject of hadronization and how it's implemented in perturbative calculations. Now, there are many ways to include hadronization, and what's done in high energy physics falls into two categories. If we have a perturbative event generator, such as Pitty or Herwig, the type of fragmentation that's typically used is a string fragmentation or a cluster hadronization. Guessing that cluster hadronization perhaps would be something a bit more similar to a coalescence model, maybe. I mean, that's a very, kind of tenuous statement. On the other hand, string fragmentation is based on the idea of string breaking. Both of those models have their advantages and disadvantages, summarized in this table. In general, I'm left with the impression that the string fragmentation captures a little bit more the correlation between soft particles when it comes to truly non-perturbative phenomena, such as multiple parton correlations or how a baryon would be correlated to a strange quark. String fragmentation will generally do a little bit better. But this is not the way in which fragmentation is taken into account into perturbative calculations. Perturbative calculations rely on the factorization formalism. For the case of hadronic collisions, the formula is written here. It's well known. You convolve the parton distribution functions with the hard part and then with non-perturbative fragmentation functions. Of course, the important part is that the non-perturbative fragmentation functions have perturbative evolution, which we can calculate using DIGLAB. Now, what are those non-perturbative fragmentation functions for the case of heavy quarks that have been used in the community or are being used now? So the first calculation of a fragmentation function into heavy quarks, into heavy mesons, charm quarks going to d mesons or bottom quarks going to b mesons, was done by Peterson and collaborators. And the form is very simple. If you want to know how it was actually done, all that they did is to evaluate the energy difference between the initial and final state in terms of the momentum fraction z, that's the amplitude, square the amplitude, and then supplement 1 over z here in front is the longitudinal phase space. And that's how this function was calculated, simply from the energy differences between the initial and final state. And actually it was shown to work reasonably well on the case E plus E minus annihilation. A more sophisticated calculation of fragmentation functions in perturbative QCD was done in heavy quark effective theory developed by Bratton and collaborators. That's Bratton, Yuan, and Chang in the early and mid-1990s. And the way in which the calculation goes is now we actually have to write down the lowest order Feynman diagrams for the production of a heavy meson in the final state. And we have to consider the different channels. The way in which the calculation really proceeds is to have a pseudoscalar, vector, or tensor final states. We can calculate those, and then the actual d mesons, whether it would be a d0 or d plus or d sub s, is a linear combination with well understood coefficients of those different fragmentation functions that are computable. Those depend on a parameter R, which is the effective mass of the light quark divided by the mass of the heavy quark, and on the square of the wave function in the origin. The mesons were assumed to be point-like. Now, with Rishi Sharma and Ben-Wei Zhang, we went away a step further. We, in fact, included the fact that the mesons have a finite width. We calculated this width using the Schrödinger, but the Dirac equation. The light quark is light, so you cannot use Schrödinger, you have to use Dirac. And what we found is that it makes the fragmentation a little harder. So those are the dashed lines as opposed to the solid lines. And the ones that are more peaked toward one are for B mesons, and then the broader ones are for D mesons. Incidentally, FONOL uses this parameterization. And again, this is not an FONOL fragmentation function. It's due to Bratton and Clark. So I should also note that the way in which those fragmentation functions are used in FONOL and also in the community are without evolution. So what's calculated at the scale of the heavy quark mass is used. And we know that this is not exactly the case. We know that there's also effects due to the evolution. If we produce a heavy quark at higher virtuality, it will radiate. And that's what big lap evolution does. And so this is the next step that we go on to include evolution from higher scales down to the heavy quark mass, or in between. So the summation of the logarithms that arise from this radiation is given by big lap evolution. And what is shown here is the effect. So the gray lines would be the initial conditions. In this particular case, the upper plot is for B mesons, the lower plot is for representative D mesons. And once we have this radiation in big lap evolution, we will go from the gray to the blue. And as you can see, big lap evolution softens the fragmentation function. Now, the red is what will happen in cold nuclear matter, so you can ignore this, but you kind of see the general trend of softening a little bit. An even more important consequence is that even if you neglected the fragmentation of gluons into heavy quarks, big lap evolution will induce mixing, and it will generate perturbatively for you a gluon component fragmenting into heavy quarks. Now, this was done for the case of the electron-ion collider, where we looked at large BRKNX, and at DIC, we don't have many gluons. So the gluon contribution still ended being small. But if you go to hadronic colliders, especially to the LHC, we have a ton of gluons, high energy gluons in the final state, and we have to worry about their fragmentation in heavy flavor as well. And that was done more than a decade ago, first by Kneel and Knish for the D mesons and B mesons respectively. And what they found is that there is a non-zero gluon fragmentation contribution into heavy flavor. Even if at the level of the fragmentation functions, it's relatively small, it's greatly enhanced, as I said, by the fact that we have a lot of gluons in the final state. Probably the best example that demonstrates the significance of this contribution are measurements of heavy flavor production inside jets. What is shown in this figure is the distribution of D stars inside reconstructed jets by the Atlas collaboration. And you see that, in fact, the experimental data shows a growing trend toward small values of Z. And this is very different than what a heavy quark fragmentation function into heavy meson looks like. So this is the clear indication of the gluon contribution. The dashed line was the original parameterization of, I believe it was Knish in this particular case. And you see that it does an okay job, but still underpredicts the production of heavy flavor inside mesons. And so Anderle collaborators performed a new global analysis of D meson production, including the fragmentation from light gluons, and obtained a much better description. So the bottom line is that the most comprehensive description of heavy meson production in high energy conditions does include the fragmentations of gluons as well, and it can be a significant contribution. Now, let me go to the way in which one applies those fragmentation functions combined with the scat calculations. And there are different ways in which we can do the calculation. If we are going to use the full splitting functions, we cannot talk about energy loss. We have a large momentum fraction where we have a growing trend. We have gluon splitting in CC bar. These are for sure not energy loss processes. But of course, high energy physics has its way, which is well understood for decades, of including those contributions. Those are next to leading order and result calculations. And the first calculation that we did back in 2017, late 16, 17, was strictly a next to leading order calculation. This means that we calculate the contribution in PP collisions, that's the baseline contribution, up to NLO, and then the medium correction is strictly NLO. And you see, what we did is, in fact, we took the first step in the Diglett evolution equations. You know, this is not solving them completely, but just taking this first step strictly to one loop higher. And then the results that we obtain are presented here in the upper figure. That would be the, I'm guessing that's the purple band. And here, that would be the red band. And you see that scat and independent fragmentation give good description of the high PT, perhaps down 10 GeV, perhaps a little lower of this distribution. One comment that I made is that at the time, we used Bjorkane hydro, ideal hydro. Now we are using a viscous hydro by Chun-Shen, and there is a difference in the energy loss or the strength. So, you know, kind of the couplings for the purpose of the exercise that we were given should be a little smaller. Now, the next step is to go from strictly next to leading order calculations to result calculations. Unfortunately, I do not have an example at the LHC or RIC for the quark-gluon plasma, but the technique is exactly the same. So this is a calculation for the case of the electron-ion collider, and this is full in-medium evolution of the fragmentation functions. What I'm showing in this figure is what happens to the fragmentation functions of light quarks to light particles like pions, charm quarks to d mesons, and big quarks to b mesons. And the fragmentation functions for pions are almost always suppressed, except for, you know, the additional gluon emission at very small values of z. But for charm quarks and big quarks, there is transition from suppression to enhancement because of the typical bell shape, and then further contribution from additional soft gluons at very small values of z. One can define, in fact, nuclear modification ratios, just like in the QGP. Here it's a little bit more sophisticated. There is a normalization by an observable that would depend only on nuclear shadowing, so that we are sure that we have final state effects. And if we look at the right kinematics, which is typically smaller center of mass energies and forward rapidities, we in fact can see as a function of PT, that's the transverse momentum relative to the collision axis, and as a function of the fragmentation fraction, significant modifications, even in cold nuclear matter. Once again, the exact same technique can be applied to the quark-gluon plasma. We simply haven't had the time or chance to do it. And so finally, there is a third way of implementing those SCT calculations. That's the traditional energy loss. In order to do traditional energy loss calculations, we have to take the soft gluon emission limit and calculate the spectrum of emitted gluons, then constrict the probability density that the heavy quark will lose a fraction epsilon of its energy due to multiple gluon emission. And those are examples of probability densities at several different energies. And finally, implement them in the calculation of hadronic cross sections. Now, there are two ways to do this. You know, the energy loss is the intermediate step between the hard production and the fragmentation, and we can associate the integral either with the hard protonic cross section, in which case we quench the partons and then fragment, or we can associate the integral with the fragmentation function, in which case we have a medium modified fragmentation functions. Because we had to produce the quenched partons to begin with, I chose the first method. So what you see in this figure is the question about the exercise, that's the homework assignment. And you see the suppression of charm quarks as well as the d mesons using, the very first just Bratton and Yuan fragmentation functions without evolution. The solid lines are the quarks, the dashed lines are the mesons, and as you can see, as they all correctly pointed out, at high PT, the suppression of mesons is slightly smaller than the suppression of heavy quarks, but once you go past the inflection point here in the distribution, of course, the row is reversed. It's just the shape of the spectra and the shape of the modification. Also, for this purpose, the more relevant, because we're using Chun-Shan's hydro, the more relevant value is G equals 1.8. And, I haven't had, as I said, the chance or ability to do a proper figure, but I tried to put this line as accurately as possible by hand in PowerPoint. And you see that it describes the spectra measured by Elise. It's perhaps on the lower edge of the experimental error bars. Now, if we go to the second assignment and see what happens to the V2, we calculate this, using the difference in the suppression along the short and long direction in this asymmetric distribution of matter. And here are the results. Once again, the solid lines are the quarks, the dashed lines are the mesons. Once again, there is a small difference between them with changes at the inflection point. And, kind of the typical values that you can get at most are about 5%. Asymptotically, however, this does not disappear at high PT. You have on the order of 3% V2, even at 100 GeV. As we go down to low PT, the V2 disappears because, as I said, it's proportional in the fragmentation picture, strictly proportional to the suppression and the difference in suppression. So if you don't have large suppression, you cannot generate large V2. And once again, by hand, I've put the results here on the experimental data. And you see that above 10 GeV, the perturbative calculation agrees with the measurement, but of course, it's very far away from, about 15% V2 that was measured by Elise. And with this, I'm done with today's presentation. Thank you.
Thank you very much, Ivan, for a nice presentation. So Xinian has a hand up already. Xinian.
Oh, no, I'm sorry. That's I did not load on my hands from last time.
Now we can take questions. Rob?
Yeah, just maybe not directly related to that talk, Ivan, which is of course very instructive, and I learned a lot, but what happened to your collisional dissociation model? Is there still a place for that in your SCET framework?
In the SCET, no. In the SCET framework, no, because the SCET framework is just a perturbative calculation of the radiation. I mean, kind of in the SCET framework, we can also compute the dissociation. It's based on transverse momentum, the transverse momentum broadening of the mesons. And I did intend to put a note on this, and I forgot. So a characteristic feature of the dissociation model, so what happens is that if we try to perturbatively estimate the formation of D mesons and B mesons, the formation ends up being inversely proportional to the mass of heavy quarks and heavy mesons. So D mesons form early and B mesons form even earlier. And if this is the case, then they can be dissociated in the medium. This is something that we calculated, 15 and 10 years ago. A characteristic feature is that the suppression then of D mesons and B mesons ends up being quite similar. And that's what early measurements observed. So later measurements at the LHC seem to see a difference until about, I think, 10 GeV, and Tianji will correct me if it's up to higher, in the suppression of B mesons and D mesons. So it seems that, the pertonic interactions are more relevant than the case of the dissociation. So I still think that theoretically it's a very interesting calculation. It's just kind of much more involved. You have to calculate energy losses for any number of paths. because the formation lengths will depend on, kind of the boost for the case of the mesons. It's just much more complicated to calculate. But at least at the LHC, it seems that this is perhaps not the most relevant. But I still like the dissociation calculation very much. It's just very difficult to do.
Oh.
Can I ask a question?
Yes, Ivan, I'm not sure.
Yeah, Paul first, then Andrea.
Oh, sorry. Yes, Ivan, usually when we take fragmentation, we evaluate them basically at rather low scale, because the picture we have is that you first have this kind of radiative energy loss, and then at late time, then basically you fragment. But you had this picture where we could also make the DGLAP evolution of those fragmentation function, and I did not quite understood why they are good for. I mean, this fragmentation function at large virtuality. Could you tell me again a bit?
No, okay. So kind of the DGLAP, when you do the proper DGLAP, right, in the vacuum and in the medium, you are in fact doing all of those radiations. It's just that it's not soft gluon radiation and soft gluon emission and energy loss. It's the full-fledged kind of evolution from the scale of the hard collision down to the low scale near the mass of the heavy quark. And so doing it this way, or like in analog calculations, taking the first step, that would be a proper framework. When you go to energy loss calculations, in those calculations, if you do the gluon emission, then at the very end, if you assume that this indeed has taken away your virtuality, then you can apply, I assume, just the initial conditions, kind of the fragmentation function in very low scales, as I've shown here. That's exactly what's done in the homework exercise. I'm still not 100% sure theoretically whether kind of the energy loss does all the proper evolution down to the lowest scales. I know that if you do it in DGLAB, that's exactly what you do.
But if you do it in DGLAB, then in the kernel you have also to put something for the induced radiation, correct?
Absolutely. So okay. So I mean, that's exactly what's done. So the blue line would just be kind of the vacuum evolution. And then, you know what the vacuum Montarelli-Spirilli splitting functions are. They're found in textbooks.
Yeah, sure.
And if you calculate the in-medium splitting functions, which are also found and verified in the papers, it's just that they're complicated. And if you have to evaluate them numerically, then you go from blue to the red. So that's the additional evolution. That's exactly what's being done.
Thank you, Ivan.
You're welcome.
Andrea?
Yes, I have a question perhaps similar to the one raised by Paul, in the sense that I have not fully understood the comment concerning F1 LL fragmentation functions and the approach, and in particular its connection with the rest of the discussion in which the energy loss was introduced, in the sense that if you're simply interested into the PP physics, let us say, I think that F1 LL is consistent in the sense that it calculates the QQ production as a result of a full evolution, and so at the end it is justified employing a fragmentation function which has no scale dependence because it is evaluated at a very small virtuality, let us say. So and by the way, I think that also the mechanism of production of gluon splitting into a QQ pair is included. But now I want to understand better the connection between what you said concerning these aspects and what you are doing, in the sense that what you want to do is to do something which allows you to include into the production itself, also the from the very beginning the medium energy loss. So I missed this connection between these two aspects.
Well, okay, I probably did not understand. So you're defending the way in which, you know, the first part of your statement is you're defending the way in which FONOL does it, and that's fine. If they have performed an evolution in the final state down to a low scale, then that would be consistent, all right? And so the second part is the part that I did not understand. I don't want to do anything, I've done it. Right, so that's the first statement. And so what I'm trying to explain is that if you calculate the full parton shower in the medium, you cannot include it as energy loss. You have to include it either as a fixed order calculation, as was done for the case of the LHC, or as a recent medium evolved DIGLAB, which we have done this for the case of the electron-ion collider, because that's what we've been working on. If you want to make connection to the energy loss approaches, you have to take the soft gluon emission limit, in which case you implement it as energy loss, not as DIGLAB. There is connection between the two. We've been able to prove now for more than 5 years ago that if in DIGLAB evolution you take the soft gluon emission limit, those two equations which are coupled equations, will decouple, and you only have diagonal splittings. Those diagonal splittings have a simple form, and you can solve those equations and show that the solution is a suppression proportional or dependent on the energy loss. So there is a connection, clear connection between them. What I'm saying is that if you want to use high energy physics techniques, which are used, to do precision calculations, you do it one way. If you want to use do energy loss phenomenology, you do it a different way. And there is a connection between two that one can understand.
Okay, thanks a lot for the discussion. So I suggest we move on to the next talk for the time.
Okay, thanks.
So, thank you, Ivan. All right, so let's move on to that mode group. So I believe Roland is going to present. Please go ahead and put the slides.
Okay, hi. Let me share the screen. Okay. Oops. Okay, can you hear me well?
Yes.
Yes.
Go ahead.
Okay, cool. Thank you. So thanks again for the invitation. Today I will address the hadronization aspects in the DAB mode, and I'm quite happy to do this because I never had the occasion to discuss the hadronization with let's say specialist people and not just interacting with papers. So okay, so I won't present again the basics behind DAB mode, but I will just add that after hadronization, we don't use any hadronic rescattering. Okay, so for the hadronization, the idea is that each EV quark propagates in the medium until it reaches a medium cell where the temperature is lower or equal to a certain decoupling temperature that we take to be 160 MeV. And then we use an hybrid coalescence plus fragmentation model. So we were inspired in our work by a work from Shan, Guan Yu, and Stefan in 2015. But there are still some differences, and I think I will try to explain how these differences might generate this really high peak that we have as compared to the other models. Okay, so for the fragmentation first, we use the simple Peterson fragmentation function, as you already saw it several times today. So I would just say that for the parameters that enter this function, we try to reproduce the D0 and D Mesons phononal spectra in PP to fix these parameters. Okay, so for the coalescence, we use the instantaneous projection of states modelization by Dover and Al that you also saw many times today. So the idea behind that is that, for example, for EV mesons, we have some coalescence probability that are given by this formula here, with n being the global normalization factor, Fm the probability density, which correspond to the projection of the two quark states onto the meson states, Nq, which is the momentum distribution of the light quarks at hadronization, and the last term is the conservation of momentum. So in more details, for the distribution of light quarks, we use the Fermi-Dirac distribution in a medium cell frame. And this distribution depends on the local medium cell velocity, which implies at the end that our coalescence probability will depend on the local flow. Then for the probability density and the projection of the two quark states onto the meson states, we use only the S-wave relation that is given, that is showed here, where there is the relative momentum of the two quarks in their center of mass frame, and the relation is given by a simple harmonic oscillator model for all the meson states, with a common sigma parameter. Then there are two factors in our relation. One is the usual quarter spin isospin statistical factor, and one is a new thermal factor term that we had by hand, and that I will develop and explain in a few slides why we added this. Okay, for the baryonic side, it's pretty much it's quite easy to extend this relation. So we obtain this larger relation here. We use the same global normalization factor as we used for the mesons. And okay, for the probability density now, it's about combining the two light quarks and the EV quarks. And I will just tell you a bit more about that in one slide. For the light quarks distribution, we use also the Fermi-Dirac as we use for the meson. Okay, so I will do a little parenthesis or footnote about that, because I observed something that I wanted to discuss with Shanshan, Guangyu, and Stefan. So I will just present a bit what I want to discuss with them. In our model, we use this relation for the probability density for baryons with two relative momentum. So the idea of this is that you first combine two quarks, and then you combine their center of mass with the third quark. And then so we obtain this formula here for the relative momenta. And it includes a dependence on the mass in our relations. And there is also this in many papers. So what I observed with this and what I tested is that if we change the ordering, the combination ordering, with this formula, there is no difference in the final results. It means that you can first combine one light quark and one EV quark, and then with the third light quark, or another way around, and at the end you have the same. But in Shanshan, Guangyu, and Stefan paper, what they use is a formula where the mass is replaced by the energy. So you obtain this kind of relation here. And what I observed, and I would like to better understand this, is that if you use these relations, you don't have this invariance with the combining order, which means that at the end, the coalescence probability is not the same if you combine, for example, the first two light quark first and then with the EV quark, or if you combine an EV quark and a light quark with the third light quark afterwards. So that's my little footnote about that. And so if Shanshan or Guangyu or Stefan could ask a question if we could discuss this later, it would be nice for me. Okay, so now let me introduce you these new thermal factors I will tell you about. So what was the problematic? Within the basic coalescence model, which I mean that is that without these thermal factors, the prompt D plus over D0 or the D star plus over D0 ratios are only based on the color spin isospin factors, with the rest of the probabilities that cancel out. So for example, here you have the D plus D0 ratio that we developed. And what we see is that it only depends on the GD, GD and GT star color spin and isospin factors. And at the end, we obtain a value of 0.32. Sorry. And actually, this value is quite different from the experimental value that seems to be within 0.45 and 0.50, which actually seems to be quite universal across over the collision systems, which is quite nice because it seems to tell us that there is maybe a common underlying mechanism in all this system, all these collisions. So when I saw this difference, I was thinking that maybe we could consider, for example, different radiuses for the excited states, or maybe introduce the energy difference that was at stake between the energy states and the ground states to try to improve these ratios at the end. So let me show you first the proposition that we arrived at the end. It was to add these new thermal factors that writes in this way. So it's an exponential of the difference of mass between the excited states and the ground states, and that we only introduce between energy states of equal quark flavor content. So for example, for the D star 0 state, we had this factor here, which is the exponential difference of the D star 0 mass and the D0 mass. So now, not only there is a spin hierarchy between the energy states, but also a mass hierarchy. And at the end, what we observe is that it makes quite a nice difference when we compare to the experimental values of the different ratio. So I summed up here in this table. So for example, in this way, for the D plus D0 ratio, instead of obtaining 0.32, we obtain 0.45, which is much closer to the experimental values. So we get a better matches. So another additional positive effects that we get with these thermal factors is that we get a natural justification of the non-consideration of more excited states in our model, such as the Chi equal 2 Mesons or the Chi J equal 5 halves variance. But also, it's a natural justification to not consider antisymmetric states, like the one I just cited here, because all these states are not suppressed by their larger mass. Okay, a few comments about these thermal factors. The motivation to add them was at the origin purely phenomenological, which means that we wanted to improve the ratio fits and the coalescence probabilities that we obtain at the end. But of course, the problem is that we don't have any theoretical justification for them, so we need to explore this better. Another nice test that we could do with this thermal factors is to study, for example, the lambda C over D0 ratio that we cannot do now because we are limited by our way that we fragment with the Peterson fragmentation function. So just to tell you, we also tried an alternative to these thermal factors. We tried to use a larger to explore or to use the larger radiuses that we have with excited states by increasing the sigma widths for the excited states. But what you observed at the end is that it was not going in the good direction and not at all going leading to good results. That's why we kept these thermal factors. Okay, so let's now see a bit about this global normalization factor that we use in the coalescence model. So first, I need to tell you that we consider all the Meson and baryonic symmetric ground and first excited states, but that we don't consider the higher excited states and the p states. As I told you, it seems that we can neglect them with our thermal factors. So, and this global normalization factor is often chosen such as to obtain a coalescence probability equal to 1 when the EV quark momentum is equal to 0, which means that we assume it is assumed no fragmentation at 0 momentum. And at the end, people obtain this kind of probability distribution as a function of the EV quark momentum. But when we explored this, we thought that it was not really justified because, of course, in PP collision, you have fragmentation even at a very low momentum. And moreover, it seems to us a bit weird that if an EV quark with a very low momentum as compared to the fluid momentum, if you have this situation, it was weird that it had a probability of coalescence of 1. And at the end, there was such a big difference between the momentum of the light quark and the heavy quark. So instead, we assumed that another thing. We assumed that the coalescence probability was maximal and equal to 1 only when the velocity of the EV quark was equal to the fluid velocity. So in this case, the coalescence is maximal when the EV quark is moving together with the light quarks surrounding the EV quark. So when we do this, we obtain this kind of coalescence probability distribution that we have here. So I will tell you a bit more about this variety of coalescence probabilities. So on the left, you have the case of C giving any hadrons, and on the right, you have C giving the direct D0 mesons and the direct lambda C. So few observations that can be made. One pretty basic is that with a larger medium cell velocity U, you tend to shift the maximum of probability to larger EV quark momentum. So for example, when we go from U equals 0 to U equals 0.6, you see that the peak is shifting. Then there is also a dependence on the angle between the EV quark velocity and the fluid velocity. What you see is that it is maximal in our case when the angle is 0, but when we get a certain angle, you see that the coalescence probability is decreasing quite a lot. Yes, okay. Okay, one another thing is that what we also observe is that when the fluid velocity is increasing, what we observe is that the meson production from coalescence tends to decrease, whereas the baryon production increases. So you see, for example, here for the D0, you see that the production decreases for the D0, but that for the lambda C, actually the production increases. Okay, so at the end, now that we have both this coalescence and fragmentation, we use a simple Monte Carlo procedure to decide either we do a fragmentation or a coalescence and into which meson or baryon. At the end, if we have a coalescence, the hadron momentum is given by the sum of the EV quark and light quark momentum. So I think now we can explain why we have such a higher peak with DAB modes. I think it originates from a mix of the thermal factors that reduce the probability coalescence of excited states as compared to ground states. And the fact also that we use a global normalization factor, such as it is equal to 1 when the velocity of the EV quark is equal to U, which means that both, and at the end, both of these points mechanically increases the prediction of ground states when coalescence probability is significant. So Here it was the D0 was studied. As it is the ground state, it is mechanically increased by our formulation. So at the end, I just wanted to show you some of the results we got with this and the difference between the basic coalescence and the use of extra-thermal factors. What we saw is that with the use of thermal factors, we get a smaller suppression at lower PT as compared to the basic coalescence model. You see that we go from dashed to solid lines here. And that if we compare what we obtain with fragmentation only and coalescence, or fragmentation plus coalescence, what we see is that, of course, we obtain better fits to data, and that the coalescence effects extend up to approximately 8 GeV in the case of the area A. For the V2, what we saw is that the thermal factors tends to a bit increase the V2 at low PT. And that as compared to the fragmentation only, when we add the coalescence, we see that we increase also a bit the V2, and we observe a shifting of the peaks at low PT. And that also that the coalescence effects extend up to 15 GeV approximately. So same idea for the V3. I will just go now to the thank you and tell you that all the details and analysis on this hadronization aspects can be found in this paper. Thank you very much.
Thank you, Roland. So can take one short question and short answer. Anybody? I didn't see any hand yet. Oh.
Yes, Roland, I think, but this should be probably discussed later today. But when people mean that they have a largest probability of coalescence at P equals 0, it is always meant assuming a fluid cell at rest. While if they are in the lab where fluid cell is moving, then of course the maximal of the probability should also scale with the velocity. I think it is really what is in the most of the models.
Yes, it's true. It's true. But then also, you're right. But what happens usually is that in this case, the coalescence probability gets higher than 1 when you have a moving fluid, and then there is this saturation that people usually takes, which for me is a bit is not a good feature.
No, this is something else. But what I wanted to say is to advocate that this specific feature of the model might be responsible for this kind of peak that we see together as compared to the other models. This probably I would not go as far. At least we would have to discuss a bit further.
Okay, you meant sorry, this kind of peaks, or
yes.
Okay, yeah. For me, it's when the fluid is moving at pretty much at the same speed as the EV quark, not at 0.
Yeah, what I wanted to say is that I guess that other models have this feature as well.
Okay, okay, yeah. Yeah, of course, but what I was discussing is not that there is a peak. I was discussing why in our case it's much higher than the other models.
Mm-hmm. Yes.
That's what I was discussing.
Thank you, Roland. So for the interest of time, let's move on to the report from Torino Group.
Thank you.
So I assume Andrea is going to give the report.
Okay, let me just share my slides.
Yes.
Okay. Okay, I will try to be quite fast, since I will just focus on the hadronization stage of our transport setup. And the idea we had a few years ago was essentially to couple a Lund-like model of hadronization to the transport stage of our Poland code. So what we do is to at hadronization, the freeze-out hypersurface, to couple the C quark at the end of the evolution in the medium, with a light parton from the medium, which is extracted from a thermal distribution and eventually boosted to the lab frame. Then we construct a string, which is then given to PITIA to simulate its fragmentation and produce the final hadron. So typically our process is a process of 2 to 1, where this one is an excited string, which then fragments into n particles. And originally the model, and that's the reason also for this cartoon, was used also to study the correlations between the hadrons, the mesons, and the light hadrons. But just to give some more details, what one has to do is to identify a freeze-out hypersurface by setting some typical decoupling temperature for the heavy quarks. Then once heavy quark crosses such a freeze-out hypersurface, one looks at the form velocity of that fluid cell, and one extract then a light quark on the anti-quark, depending essentially on the mass of the particle, of the mass over temperature ratio. So since clearly it is more likely to recombine with a light quark, with a U or D quark, than with a S quark, just due to the mass difference. And then one extract a thermal distribution for the momentum in the local rest frame of the fluid, which is then boosted into the lab frame. So at the end, one can join these two partons, the heavy quark and the light anti-quark from the medium, to construct a string with these routines of PITIA 6.4. And this excited string, which is a color singlet of possibly also large invariant mass, is then fragmented employing this pi-exec routine of PITIA, which simulates the fragmentation according to Lund model, and then one can store the information on the particle one is interested in. Just a few comments. We don't have to worry about normalization, about the relative momenta of the partons, about how close the velocities of the heavy quark and of the light quark are, because I mean, in this setup, this recombination with some thermal partons occurs with probability 1. And by the way, this is something which occurs also in any simulation of elementary processes in PITIA, in which at the end the high energy parton is reconnected with some other partons from the underlying event. This is because one does not need to form a bound state, a bound hadrons, and to worry about the overlap with the wave function of the meson, but one simply form an excited intermediate states, which then will eventually decay. And it is important also to stress that in this setup, the production of strange demesons or of heavy flavor baryons is suppressed, because in any case the mechanism of hadron production is still string fragmentation, and then clearly exciting a SS bar or a quark diquark pair from the vacuum is less likely than exciting a light QQ bar pair. And so we are not able, with such an approach, at least in its standard implementation, to account for modifications of heavy flavor hadrochemistry, which are becoming more and more relevant. So which is the effect on the observables, at least for what concerns the kinematic distributions of particles that you produce? Well, this can be assessed by looking at the differences in the REA and V2 given by the different hadronization procedure. You see in green here the REA of at the quark level, and you see that you can easily compare the effect on the REA of implementing hadronization via vacuum fragmentation, which are the red curve, or via in medium recombination supplemented by this string fragmentation, which is the blue curves. And you can see that at the intermediate momenta, both for the REA and for the V2, I get a significant amount of flow inherited from the light partons from which we recombine. And this is also due to the fact that there is an exact implementation of space momentum correlation by construction in the model. On the other hand, and this is a nice feature of the model, at very high momentum, essentially one recovers the result of standard vacuum fragmentation, and this also arises naturally by construction, since for a very high energy parent parton, it doesn't make much importance where the other endpoint of the string sits. And we can quantify even better this by considering this HAA in these two different definitions which were employed by this team. One is the ratio of the REA, and one is the ratio of the spectra after and before hadronization. And as you can see, the message again is that at the intermediate momentum, I have an effect. I have essentially, I acquire some radial flow from the light thermal partons, and on the other end, at a large momentum, the effect is simply a suppression of the PT distribution, which is typical of a fragmentation process applied to a steeply falling parton spectrum. The effect of space momentum correlation is always important to enhance the Vn harmonics of the mesons, but it becomes particularly significant in cases in which the underlying Vn coefficient of light partons is not so large, like in the case of the directed flow. And in this case, you see that even if the directed flow of light partons is very, very small, in any case, this space momentum correlation leads to an increase of the V1, also as an effect of hadronization. In summary, just to summarize the main features and the main advantages, but also the limitations of this approach, I can say that we have by construction an exact conservation of energy and momentum through this 2 to 1 to n dynamics, and in which this string, this intermediate string is like an excited resonance of invariant mass m, and this allows us to conserve exactly energy and momentum. We have in our approach built-in space momentum correlations, and this, as we have seen, significantly enhances any flow signal once going from heavy quarks to heavy flow hadrons. And we have a smooth approach of the results to what one obtains with vacuum-like fragmentation at IPT. since, as I was mentioning, for a very high energy heavy quark, it doesn't really matter whether the second endpoint of the string is a thermal parton, like is the case in this implementation in nucleus-nucleus collisions, or it is simply some quarks from the underlying event, like it could be the case in standard PITIA simulation of proton-proton collisions. And on the other hand, a limitation is the fact that we don't have any medium modification of heavy flavor hadrochemistry, since at the end hadron production still occurs through string fragmentation, for which we have not modified the standard PITIA routine. And clearly in the near future, we should include some different mechanism to simulate the decay of low invariant mass clusters, allowing allowing heavy flavor hadrons to inherit the quantum numbers of the light parent quark or die quark from the medium. So in order to reproduce also the enhanced production of this ABS or lambda C baryons. Okay, I am basically done, and I thank you for your attention. And if you have any question, please ask.
Thank you very much, Andrea, for the talk. So it's time for questions. Anybody? Ralph?
A quick question. The string fragmentation that you have in your approach, do they know about the higher excited resonance states, or is it just a generic energy excitation?
No, essentially, the information that you have to give to PITIA is simply the information on the four momentum components of the parton with which you recombine. Then what is inside the PITIA is simply the list of hadrons, which is or resonances, which is included in the standard implementation of the public version of the code. Then, of course, one could try to modify its default set of particles and resonances by modifying a bit the code and including features which were not included at the end of the release at the time of the release. But so
no problem. So the answer is yes. Your approach knows about the excited resonances, so that's good.
Oh.
Yeah, so maybe some specialists in coalescence can correct me, but I thought naively that the excess of lambda C in AA more or less comes from the fact there is an excess of like quarks, and then basically this excess is larger than in PP, and this makes this process more abundant. And then if it is the case, couldn't you somehow implement also a string that would be made of one C quark and of some kind of die quark or some partners? And
look, you're perfectly right, and this is something which I wanted to do. But the problem is that at the end, the heavy flavor hadron that you produce is a heavy flavor hadron in which the heavy quark recombines with this string mechanism with the particle that you excite from the vacuum. That's why I was saying that in order to make the heavy flavor hadron inherit also the quantum number, so in this case the baryon number of the particles with which you recombine, it is necessary probably to modify a bit the way in which small invariant mass strings are hadronized and taking into account something that you like what you were mentioning. By the way, for instance, Ervig has two different mechanisms to let us say, fragment low invariant mass clusters and high invariant mass clusters, while PTI is a unique recipe. So probably it could be the case to think about something different in order to be able to reproduce what you are saying.
Yeah, in what I was thinking, the string does not necessarily fragment because there is a low invariant mass.
Exactly.
Yeah.
Exactly.
Any other questions? I didn't see any hand. Okay, so this means that we can end the section 5 on time.